Stand by for a journey no one would ever dare take. To the sun. Above the protective blanket of our atmosphere, and you'd be exposed to the full blast of the sun's lethal radiation. The ultraviolet would sunburn you in seconds. Next, skin cancer, then eye cataracts. Your hands would be hot enough to melt lead, yet in shadow, your feet would be an ultra-deep freeze. We're heading to the superheated heart of our solar system. Here, invisible forces conjure up hoops of fire so big they'd swallow the earth. Where solar flares spear space with bursts of raw energy. Put planet Earth next to one of these, and in seconds it would vaporize. Stalks of hot hydrogen. This red prairie is invisible to us on Earth, as we're dazzled by the bright glare that lies beneath. Here, plumes of heat rise and fall, each one the size of Texas and 1,000 miles deep. And deeper still, at the nuclear heart, it's 30 million degrees Fahrenheit. But planet Earth is just the right distance from this inferno. While other planets either freeze or fry, we, at 93 million miles, sit in the comfort zone. Any closer, and the oceans would boil away. Further out, and Earth would be a frozen wasteland. Turn off the powerhouse, and in just a few months, we'd be under ice. We owe our lives to this savage sun. The sun sustains life on Earth. Its warmth drives our weather, lifting water from the seas and moving it over the continents. Rain and snow make lands fit for life. But our sun is not only warmth, it's light too. The miracle of plants is their ability to use sunlight to grow. In growing, they create another miracle. Using photosynthesis, plants convert water and carbon dioxide into carbohydrates, which releases oxygen. Like plants, animals also harvest the energy from the sun. The warmth in every animal's body was once sunlight. Without that warmth, creatures like the crocodile don't have the energy to digest their food. A thermal imaging camera shows hot spots, the humps on an alligator's back, that have evolved to soak up the sun. They absorb heat through the skin and pass it on through the bloodstream. Food would rot in a cold gator's stomach. We too like to lie in the sun, and when we do, we get more than just a suntan. Our skin starts making ingredients for the vitamins we need to survive, using chemical reactions that are triggered by the energy in sunlight. We owe our lives to this massive natural power plant. It uses as its fuel the simplest chemical in the universe, hydrogen, the lighter-than-air gas that once lifted airships to the skies. 1937, 70 tons of hydrogen float the Hindenburg over New Jersey. But a spark strikes. The gas burns in a chemical reaction. But that same hydrogen, fused together in a nuclear reaction like that on the sun, would have devastated New York. That's why the sun is best viewed from a safe distance. Big Bear Mountain Lake, where the cool, tranquil air is unruffled by the heat haze. The telescope in the Big Bear Observatory can filter out the sun's glare. It tunes into just one specific color of light, and a new sun is revealed. No longer a blinding disk. See only the light given out by hot hydrogen, and the sun's features suddenly come into view. These features reflect the sun's mood, moods that in turn affect our Earth. The small round specks are cooler areas, sunspots that sit within a broiling surface. Flares, lesions that open up, shining brighter and hotter in the hydrogen light. These hot spots are some of the lighter patches. Massive filaments, loops of gas arching up over the surface. Seen head on, they are the dark lines that snake over the face of the sun. Those same features, when seen against the rim, are called prominences. They curve out, big enough to girdle the Earth. The sun's secrets are betrayed by the range of radiation it sends out into space. There's much more to sunlight than meets the eye. Thanks to the internet, you don't need to visit a telescope to study the sun. Professor and author Ken Lang works from his home in Boston. He's devoted most of his career to understanding what makes the sun shine. The secret lies in the sun's ability to squeeze hydrogen atoms so hard that they fuse together and make helium.
The sun shines by nuclear fusion, the fusion of 4 hydrogens into 1 helium. First one hydrogen fuses to another, then another, and a fourth. But the helium weighs less than the 4 hydrogens that went into making it, so what you get out is less than what you put in. That mass difference is energy that powers the sun.
A few pounds of matter becomes energy in an H-bomb. But every second the sun releases the same energy as 1,000,000 H-bombs. Yet there's a force that stops it blowing itself to pieces. Gravity. It's strong enough to keep the nuclear monster in check.
Gravity compresses the sun, making it heat up inside. The particles move faster, and the nuclear fusion proceeds at a more rapid rate. That produces an outward pressure that makes the sun expand and cool back down again.
But when fusion forces the sun to expand, gravity reins it back in. The core heats up and nuclear fusion increases. And so the pendulum keeps swinging between gravity and fusion. It's like a tug-of-war going to and fro, but with no winner. It all began 5 billion years ago, when gravity pulled in a cloud of cosmic rubble. At the core, getting denser and hotter, gas and dust fused together. Comets streaked towards the newborn sun. Today, the Hubble Space Telescope sees the same process going on. all across the sky. Our sun is just one of billions of stars. Hubble zooms in on them and shows us stars of every age in a life cycle that links them all, for stars are born of other stars. A massive star explodes and litters space with its embers. Its death shroud joins the debris from countless other explosions. These ashes will become the seeds of new stars. The Eagle Nebula, a crucible of creation. Massive clouds from long-dead stars. Inside, stars, planets, perhaps even life, all hover on the brink of birth. But in the gas and dust that makes up the Orion Nebula, gravity has already pulled in the debris and ignited the celestial fires. New stars with billions of years to shine. From the universal star story, back to our sun.
What you see on the sun depends on how you look at it. In addition to the visible colors, there's invisible X-rays, ultraviolet rays, infrared rays, and radio waves. The most interesting parts of the sun are at invisible wavelengths. They provide a new perspective.
Just like tuning in a TV, each new wavelength gives a new picture. Since most of this invisible radiation is absorbed in the atmosphere, we send up satellites.
5, 4, 3, 2,
Cape Canaveral, December 1995. Satellite SOHO hangs in space at a special point, 1,000,000 miles out, where the Earth's gravitational pull is just as strong as the sun's. This solar-powered, solar observer ends up balanced between the two. NASA, Goddard Space Flight Center. Scientists here studied the images that SOHO sent back to Earth for several years. But in 1998, Mission Control lost those images when SOHO spun away from the sun and its power failed. All they could do was wait and hope the spacecraft would rotate back to face the sun. Slowly, it did. Pictures from the SOHO gallery. If our eyes could see ultraviolet radiation, then the sun would look something like this. X-ray vision shows bright, hot patches. Look in the light of helium, and a turbulent rim is revealed. Here, gases are moved by an invisible force. Magnetism, that's what shapes the sun. The patterns we see on the sun are the same as the magnetic field lines around a bar magnet on Earth.
Magnetism molds, shapes, and constrains everything we see on the sun. It energizes powerful explosions. It heats the solar corona. Invisible magnetism rules the sun.
The sun is so hot that its hydrogen atoms are ripped apart. What's left is plasma, a seething fire of electrically charged particles. And wherever there is magnetism, plasma will spin. Here, nothing is still. This wild whirlwind is a solar tornado 1,000 miles wide. And beneath the bright visible surface, convection lifts massive plumes of plasma from the pressure cooker below. Deeper still, hot plasma, slave to the magnetic field, snakes into rivers of fire. The sun is constantly in motion. Maps show that the plasma moves at different rates in different layers. Red is faster, blue slower.
Electrical particles are swirling around inside the sun, faster at the equator, slower at the pole, and that difference in motion produces the magnetism of the sun.
And that can be studied at the Murtagh telescope. The heart of this observatory is a hole in a hill, with a mirror on the top. Don Jennings has come here to study the sun's magnetism. Though it never touches the earth, that's not going to stop him.
The tube that telescope is built in is supposed to be a very constant temperature. And so having it inside a mountain, it's like having it in a cave. The air inside the tube isn't as turbulent, and it gives a much sharper image. It has a mirror at the top that tracks the sun, and it sends a beam down 300 feet into the side of that mountain to another mirror that takes that beam and focuses it, forms an image right where we have our instrumentation set up.
You can see the big sunspot, and what's amazing to me is that the sunspot in the back is 2 sunspots at this time, not just 1.
And how are we planning on mapping them?
Put the slits here. And
Don and Pedro Sada are magnetic map makers. It's a tough job. The landscape and the sunspots keep shifting.
Sunspots are places where the magnetic field is very strong and the activity on the solar surface is very strong. And we want to study the structure of the magnetic fields in the region of the sunspots and also see how it changes from hour to hour or day to day.
To study the hottest body in the solar system, they must go to the other extreme of temperature.
We have to fill our instrument with liquid helium and liquid nitrogen because there's a sensor inside the instrument that needs to be kept just a few degrees above absolute zero in order to operate properly. What you see is some of the helium coming out and causing water vapor to form in the air.
But it's not just smoke and mirrors. There's a lot of serious science going on here. Don and Pedro can't measure the sun's magnetism directly, but they can see its effects. The frozen sensor will be looking at infrared radiation from the sun and measuring minute variation in its color.
Now you're ready to go.
John, do you want to put the filters in while I put the pinhole in place?
Okay.
Strong magnetic fields alter the color of some of the light from the sun. Don and Pedro know what the color should be, and by seeing how much it has changed, they can map out the strength of the magnetism around a sunspot.
Okay, Don, I'm going to focus the camera so we can see the sunspot better.
Okay, go ahead.
They've built up a picture of how the magnetism behaves
Okay.
around sunspots.
The magnetic field coming out of that sunspot is almost like a fountain. It comes up out of the center, very concentrated, and spreads out. And usually sunspots come in pairs or maybe more, and the magnetic field will come out of one sunspot, maybe North Pole, like on a magnet, and go into the other sunspot that would be South Pole.
Within the huge magnet of the sun are these other magnets. The sun's plasma traces out the magnetic field lines between North and South poles. When the sun becomes more active, the magnetism is more complex. Then, the surface is turned into a carpet of magnetic turmoil. That's what causes even more sunspots to break out. The sunspots look dark because they're cooler than the rest of the sun. Spots form where the magnetism is strongest. The invisible force field diverts the rising heat away from those parts of the surface and makes them cooler.
If you could stand in the center of a sunspot, you would see that it is slightly depressed. It looks sort of like a dish shape.
The sun's magnetic field lines stretch way out into space. Sometimes they are traced out by its hot gases and form massive loops. These are prominences. The lines of force act like invisible threads, drawing the plasma out. It can hang above the sun for weeks.
If you could stand near a prominence, you would see thousands of miles, perhaps, a loop that large with material flowing along the magnetic field. You don't see the magnetic field, you see the bright material.
Loops of gas that could stretch from Earth to Moon.
Magnetic field lines, when they form a prominence, are following a shape just like you'd see around a bar magnet. It's the same pattern. Often they start as small loops and they build up, and over a period of time they may disconnect, and material then actually flows out into space.
A massive solar slingshot hurls out millions of tons of particles. It may seem to be going slow, but this plasma is traveling so fast, it would cross the United States in less than a minute. Shock waves from a sudden, violent release of energy. Like a pressure cooker blowing off, it releases some of the sun's pent-up fury. For a few seconds, a single flare throws out as much energy as the whole of the sun. For a short while, a flare can be the hottest place on the sun, hotter even than the core.
A flare is activity, like a prominence or a sunspot, but in this case, the activity is very strong and short-lived, and it's a brightening. Very rapid brightening over a period of minutes, in which material is actually thrown out into space. The strong solar flares are actually quite dangerous because the flare throws out so much material in a short amount of time. We have disruption of radio signals, we have satellites that may go out of operation. We actually need to know when a flare goes off in order to prepare for it.
Solar terrestrial indices for 28 October follow. Solar flux 108 and Boulder A index 10. Repeat, solar flux 108.
Boulder, Colorado. This is the National Space Weather Center.
In the NOAA Space Weather Operations Center, we monitor the sun 24 hours a day, 7 days a week.
The Boulder K index at 0 hours UT on 29 October was 3. Repeat, 3.
Today, Courtney Williamson is the center's weathercaster. Others plot and map the sun's activity.
One of the things we worry about is solar flare activity.
Solar activity will be low.
Now, these bright areas are areas of very strong magnetic fields, and sometimes these magnetic fields become very contorted. When they do so, they want to release their energy, and they do that in the form of a solar flare.
8 minutes after a flare, the Earth is blasted with X-rays and ultraviolet, playing havoc with communications. 1984. all communication between Air Force One and ground control has been blacked out. By the time President and Mrs. Reagan deplane in China, the U.S. military commander-in-chief has been out of touch for several hours. There was nothing anyone could do about it. Even satellite communication was affected. In a solar storm, rays of energy fry Earth's upper atmosphere. The thin air expands, dragging down satellites that would normally orbit high above. But flares aren't the only result. Prominences may show up as bright loops on the rim of the sun. But when seen head-on, they appear as thin black streaks. And they take on a different name, filaments.
The dark features are called filaments. They sit higher in the solar atmosphere, and sometimes they erupt from the sun. When they erupt, they make their way into the solar wind and propagate towards Earth.
The solar wind is a stream of charged particles coming out from the sun. Our star constantly blows itself away, sending 1 million tons of electrons and protons into space every second. Our first clue to the existence of this wind came decades ago, from comets. 1986, Comet Halley. Touched by the sun's warmth, its ice and dust boil off. 10 years later, Comet Hale-Bopp, seen with 2 tails. One, a yellow trail of dust and dirt that litters the comet's path. The other tail, electric blue, its glowing gas, charged particles, and like a windsock, it blows in the direction of the solar wind. This tail always points away from the sun, but there are better ways than comets to see the solar wind in space. Satellites feed the screens at the National Space Weather Center.
This is solar wind density, velocity, and magnetic field.
They show Joe Kunches exactly how the solar wind is blowing.
Right now, the velocity is around 1 million miles per hour. If it were twice that, we would be in a condition that we know is related to strong geomagnetic storm activity on Earth.
SOHO can see the storm on the horizon. With a disk in the center to blot out the sun's glare, it sees the particles that are blasted out from the sun. They strike the camera's sensor and sparkle. Blast after blast of electric particles will pummel Earth's magnetic field. It takes a pounding, sometimes with devastating consequences for our planet. This computer image shows the Earth's magnetic field being blasted in 1997 by massive gusts of wind. The normally calm field, shown here in gray, rocks violently as waves of particles strike it. Blasts like these can knock out power grids. The wildly changing magnetic field acts like a dynamo, generating extra electricity in cables. Circuits trip or blow. Quebec, 1989.
This morning, 6 million people across Quebec woke up to darkness and disbelief. People at Hydro-Quebec are not positive, but they think the blackout was caused by the sun.
Darkness for Montreal, but lights for the rest of America. The particles that knocked out Quebec made it down to Earth and set off the aurorae, the northern and southern lights. High-speed electrons cascade down Earth's magnetic field lines. Like electricity making the gas in a neon light shine, they collide with the oxygen in our atmosphere, and it glows. Although the NOAA Space Ops Center has the most sophisticated solar storm warning gear, they still need the human eye to see the subtle changes. Larry Coombs watches the activity build up and knows we're heading for a big one.
In just a couple more years, around the year 2000, we're expecting to be in the solar maximum period. We can expect a lot more features on the sun than we have even today. We can expect, along with those features, to have more disturbances coming from the sun toward the Earth.
Solar activity waxes and wanes. Every 11 years or so, its magnetic field twists itself like an elastic band before it snaps over. 1985. It's quiet, with large gray areas of neutral magnetic field, the start of a solar cycle. 5 years later, the activity has increased. The spots are the poles of many magnets. By 1991, at the maximum, it's a riot of magnetic disturbance. Then, the magnetism calms down, and the solar features fade away. 5 years later, it's back to calm, and the cycle goes round again. The next solar maximum is due soon, and the Space Weather Center takes advantage of the calm before the storm.
Terrestrial conditions for the last 24 hours follow. Solar activity will be low. The geomagnetic field will be quiet to unsettled.
These city lights were once sunlight. Plants and animals soaked up the solar energy before they were turned into fossil fuels. The glint of billions of stars. Millions of nuclear engines sparkling in the night sky. Even the moonlight bathing the tree is starlight. We only see the moon because of the sun's rays that bounce off it. But storing that energy as coal and oil has taken millions of years. Is there a faster way to gather it? The amount of energy that comes from the sun is phenomenal. If we could somehow gather all the energy that fell on the Earth in one day and store it, it would supply the energy needs of the whole world for 30 years. If only we could reap that energy. When it comes to solar farming, Dave Ribb knows you've got to think big. Barstow, California.
Well, we're in the world's largest solar power facility.
Dave's got 11 million square feet of reflectors.
We make enough power here on the average for about 50,000 homes.
In his giant California field, although he grows no crops, he still manages to have a harvest.
We're collecting the sun's energy by concentrating it with these parabolic-shaped reflectors onto a central tube where we have a fluid that heats up and then carries that energy in the form of heat to heat exchangers where it makes steam.
The fluid inside the tube is oil, frying in the heat of the sun. Hotter than molten lead, each square yard of reflector gathers enough power to run 5 TV sets. From sunlight to electric lights. But even though he's choreographed 500,000 reflectors to track the sun across the sky, some sunbeams still escape Dave.
We count on about 30 cloudy days per year and more days that are partially cloudy, but that still leaves a vast majority of clear, sunny days.
Solar power will never provide all our electricity. But why try to collect the energy from a star 93 million miles away? Some people want one a little closer. General Atomics, San Diego. Welcome to the Star Factory. This is where they dare to fuse atoms.
Well, in a sense, we're like a mini star factory. We do produce some very, very hot things here, much hotter than anything else on the Earth.
Rick Lee is going into the small donut-shaped chamber where scientists are trying to make a star on Earth. He wears protective clothing to keep it clean. Contaminants at 200 million degrees would do unimaginable damage. This sun factory is the latest attempt in the 50-year dream to harness nuclear fusion. It's a monster of engineering. All this to try and replicate what the sun does every second of every day. Although he is a scientist, getting into the vessel has required Rick to perfect an art.
Well, it's a little bit tight here. Kind of like giving birth. But if I get down on my side and push my way through here, hold on, maneuver around a little bit, put my feet up here and walk down the wall, and it's really not that hard.
The sun squeezes atoms together with gravity. Rick uses another force.
We're going to use very strong magnetic fields to squeeze these particles together long enough for them to fuse. In a sense, you could think of this as a magnetic bottle.
They start off running a small amount of gas into the ring. They use electricity to strip off its electrons and turn it into electrically charged plasma. It can then be moved by magnetism.
It'll fill about this much, and then we'll turn on the electromagnets on the outside, which will produce magnetic fields to squeeze the plasma down to about this size, where the hottest part, the most dense part, will be about here, about the size of my head.
But containing the plasma with magnetism has been compared to holding jello with elastic bands. At present, they can only hold fusion for a few seconds. It's incredibly attractive to run a sun on Earth. For the fuel, heavy hydrogen will be cheap. It's a variety of hydrogen that occurs naturally in seawater. Harness fusion, and it could be a cheap source of power for future generations. Eclipse in the Caribbean. Cosmic coincidence. The moon is a perfect size and distance to blot out the sun's brilliant disk. Only when the sun is completely eclipsed will it be safe to remove these special glasses. Then it'll be possible to see the sun's secret outer coat, the corona. Although 3/4 obscured, it's still bright daylight. Daytime darkness descends on Curacao. The moon eats away at the final scraps of the sun. Almost there. Now, with the glare blotted out, the corona, the glowing white outer layer of the sun, is visible. Appearing above the sun, a pinprick of light, another at about 7 o'clock. They are Jupiter and Venus. Although the Earth is in darkness, these two planets, millions of miles away, are on the sunny side of the solar system. Down below, at 2 in the afternoon, it's as dark as night. Pictures from a different eclipse. Not all magnetic fields are closed loops. Some extend outwards and the corona follows them like streamers. The field lines run straight out into space, and just sometimes it's possible to see a prominence. On the right limb, a coil of hot gas peeping over the edge of the moon's rim. A curl of pink only ever seen with the naked eye during an eclipse. But the Caribbean eclipse is all over in just a few minutes. It's like a diamond ring as the first rays of sunlight burst through the valleys on the moon. Scientists want to see the corona every day, but eclipses are rare and difficult to follow, so they make their own. 70 years ago, at this beautiful French observatory, they had the idea to place a small disk in front of the telescope to give themselves an eclipse whenever the sun shines. They see what happens around the rim of the sun. Over 2 weeks, prominences come and go, and expulsions of particles fill the corona and add to the solar wind. It gives the sun a red halo. From outside our atmosphere, the SOHO satellite gets an even clearer picture. Combine that with an image of the sun and see how activity on the surface throws particles out into the corona. But radiation and winds are not the only things coming from the sun. Tiny particles, neutrinos, stream out from the nuclear core. A byproduct of fusion, they are like the exhaust from an automobile that can tell us how the nuclear engine is running. Sudbury, Ontario. The Solar Neutrino Observatory. For 3 years, over a mile underground, they've excavated an enormous cabin 10 stories high. The heart of the detector where they hope to catch a few neutrinos is a gigantic water tank. If our eyes could see neutrinos, they'd rain down heavier than the worst blizzard imaginable. Nothing gets in their way. Passing through 1.25 miles of rock is nothing for these unstoppable particles. This experiment needs $300 million worth of heavy water. They can't afford to buy it, so they've borrowed it. Here goes another $6 million down the hatch. They use heavy water because it gives off a tiny flash of light when it's hit by a neutrino. And that flash is what they'll look for. Different nuclear reactions give out different types of neutrino. The sort of neutrino and their number are strong indicators about which reactions are taking place. No other experiment can tell us so much about the sun's core.
Well, there are about 100 billion neutrinos passing through the tip of my finger every second, and yet with 1,000 tons of heavy water, the best medium for detecting neutrinos, in our detector, only about once an hour does a neutrino stop and produce a burst of light that we observe. By going, in our case, 6,800 feet underground, we have a large depth of rock to shield cosmic rays from reaching our detector. Otherwise, if we put our detector on the surface of the Earth, it would glow like the northern lights.
Neutrino hunter Duncan Hepburn goes to work in a solar observatory where the sun will never shine. But as well as discovering the secrets of the sun's core, this experiment will also tell us about neutrinos themselves. Know that, and you're well on the way to knowing the ultimate destiny of the cosmos. The Neutrino Observatory needs to be a very clean machine.
Everything in the world is radioactive to some degree, a low level. And our only defense is to keep the place extremely clean so there's no dust in the middle of the detector.
This underground lab is cleaner than an operating room. Duncan needs to scrub out.
Everybody that comes in takes a shower. The basic mechanism for detecting a neutrino is it comes from the sun, through the earth, and into our heavy water.
Heavy water, where the hydrogen atoms in that water have an extra neutron. That extra neutron is the target. Strike it with a neutrino and a high-speed particle comes off.
Think of it as a billiard game, and suddenly we have one ball going very fast. It produces a forward-looking cone of blue light. Therefore, surrounding the heavy water is 10,000 light sensors that are tuned up to watch the blue light and count that. This forward cone of light indicates the direction the neutrino came from. That's a very valuable signal because we can always match that up with where we think the sun is in the sky at that time.
As well as divulging the secrets of the sun, the Sudbury experiment could tell us far, far more. The most fundamental question of science may be answered here. Sparkles in the water should reveal how much the neutrino weighs. Know that, and you can forecast the future of the universe.
There are more neutrinos than any other type of particle in the universe. If they have even a tiny mass, that can influence the current expansion that has been taking place since the original Big Bang, and perhaps even create a big crunch billions of years in the future.
But whatever the end for the universe, the death of our sun will be much sooner. In 3 billion years' time, any earthly life is doomed to fry. The sun loses its balance and the scales rock between fusion and gravity. The remaining hydrogen moves to the edge and blows out, while the helium core burns brighter than ever did the hydrogen. As the sun swells, the inner planets are consumed. The ice caps of Mars melt. The larger but not so heavy sun loses its grip on the planets, and they move away. Gusts of hot wind blast the outer planets. Saturn is stripped to its core, and its icy rings melt and vaporize. Once giant, Jupiter is now humbled, overshadowed by its moon, Europa, on which the ice sheet has melted and where oceans now swell. This solar system is unrecognizable. The sun now eats itself, shrinking to a white dwarf and gorging on the elemental ashes of previous fusion. In this final phase, it disgorges vast swaths of dust, and the death shroud reaches way beyond any of its former planets. The hourglass has run out for this solar system. The sun, that once nurtured and breathed life into its children, now consumes them. It throws their ashes to the cosmic wind, there to be gathered into clouds, wherein may form new stars, new planets, and perhaps new life.